This is part 3 of chapter 13, Collgative Properties. Now, solids and liquids emit gaseous particles. These molecules may stimulate our olfactory lobes and we detect an odor. The rate of emission from the solid or liquid depends on temperature and the strength of attractive forces between the particles. The gaseous particles, like any gas, collide with container walls and cause a pressure. And we call that the vapor pressure. In a closed container, imagine we have a solution. At the surface, some particles have enough energy to escape the attractive forces in the liquid state and jump into the vapor state. So particles of vapor begin to accumulate in the gaseous state. Some of those particles are moving slowly enough to be recaptured by the liquid state. Eventually you get to a point where particles are coming off of the liquid and evaporating at the same rate that they're jumping back into the liquid. The pressure caused by the vapor particles at this point is called the equilibrium vapor pressure. So let's talk about the vapor pressure of solutions. The vapor pressure of a solvent above a solution is lower than the vapor pressure of the pure solvent. The solute particles replace some of the solvent molecules at the surface. So imagine we have a pure solvent in equilibrium with its vapor in a closed container. Particles are jumping out of the liquid at the same rate they're jumping back into the liquid. And then we add a non-volatile solute like sugar or salt, and that reduces the rate of vaporization because some of the surface particles are now solute particles. So now you're not at equilibrium anymore. Particles are jumping into the liquid at a faster rate than they're jumping out of it. So eventually, equilibrium is reestablished, but with a smaller number of vapor molecules, and therefore the vapor pressure will be lower. The vapor pressure lowering, or the new vapor pressure, can be calculated using Restos Law, which says the vapor pressure of a volatile solvent with a non-volatile solute is equal to the mole fraction of the solvent times its normal vapor pressure. So if you want to calculate the new vapor pressure, it will be equal to the mole fraction of solvent times the original vapor pressure of the pure solvent. The change in vapor pressure is going to be equal to mole fraction of the solute times the original vapor pressure of the pure solvent, the original vapor pressure of the pure solvent. So here's a question. Calculate the vapor pressure of water at 25 degrees in a solution prepared by mixing 99.5 grams of sugar with 300 milliliters of water. The vapor pressure of pure water at 25 degrees is 23.8 torr. Pause it, try it, and then we'll show you our answer. The answer would be 23.4 torr. Let's talk about boiling point. When the temperature of a liquid reaches a point where its vapor pressure is the same as the external pressure, vapor bubbles can form anywhere in the liquid, not just on the surface. This phenomenon is what's called boiling, and the temperature required to have the vapor pressure equal to the external pressure is the boiling point. So imagine you have two solutions, one pure water, the other with a solvent dissolved in it, such that the pure water at 25 degrees has a vapor pressure of 23.8 torr, and the water with a solvent at 25 degrees has a vapor pressure of 23.4 torr. Now, if pure water boils at 100 degrees C, when its vapor pressure equals 760 torr, which liquid above would have the higher boiling point? Pure water, the water solution, or would they both have the same boiling point? So we know that the vapor pressure of the solvent is 23.4 torr. And in order for it to boil, its vapor pressure has to get up to 760 torr. Pure water has a slightly higher vapor pressure. So at 100 degrees C, this will be 760 torr. But our solution at 100 degrees C is going to be a little bit less than 760 torr. And we have to heat it above 100 degrees Celsius to get its vapor pressure up to 760 where it will boil. So the water solution is going to have the higher boiling point. The boiling point is elevated when a solute is mixed in to the water. The drop in vapor pressure of a solvent in a solution from that of the pure solvent affects the boiling point of the solution, which will be higher than the pure solvent, and it affects the melting point, which will be lower than the pure solvent. This has many practical applications. For example, antifreeze in your car, so the coolant in your car doesn't freeze and damage the engine. Or adding salt to ice or snow on a roadway, which can melt the ice or snow and prevent traffic accidents. Or making ice cream by adding salt to the ice in an ice cream maker so the ice cream freezes. The drop in melting point or the rise in boiling point is directly proportional to the number of particles of solute in the solution. And here is where we use the units of molality. So here's a question. What is the freezing point of a 1.7 molal solution of ethylene glycol, which is antifreeze basically? The freezing point depression constant of water is 1.86 degrees Celsius per molal. You try it, and then I'll show you the answer. Here it is. You work it out, and you get minus 3.2 degrees Celsius. Remember that TF is the freezing point lowering, not the new freezing point. So after you calculate the freezing point lowering, you must subtract it from the freezing point of the pure solvent to get the new freezing point. 0.243 grams of a substance is dissolved in 25 milliliters of water. We're given the freezing point of the solution as minus 0.201 degrees C. Of course, since the freezing point of water is 0, then the freezing point depression is 0.201 degrees Celsius. So what is the molar mass of X with the freezing point depression constant at 1.86? Put it on pause, you try it, and come back. So we're after molar mass, which is defined as grams per mole. We are given grams, so we have the numerator already of the solute. We need to calculate moles. We use the freezing point equation. The freezing point lowering is 0.201 degrees Celsius. We now can calculate the molality by dividing 0.201 by the freezing point depression constant, 1.86. And we get 0.108 molal. So molality is defined as 0.108 moles of X per 1 kilogram or 1,000 grams of water. And here we're talking about 25 milliliters of water. So if we multiply our molality with a mass of water in grams times the 25 grams of water that we have, we get 2.7 times 10 to the minus 3 moles of X. So now we have grams, we have moles, we divide one by the other, we get 90 grams per mole. Now let's talk about osmotic pressure. Imagine a U-tube, and at the halfway point at the bottom of the U-tube, you have a semi-permeable membrane. That's a membrane in which water particles can pass through, but salt particles cannot pass through. Now let's talk about osmotic pressure. Imagine a U-tube, and at the halfway point at the bottom of the U-tube, you have a semi-permeable membrane. That's a membrane in which water particles can pass through, but salt particles cannot pass through. So on one side of the semi-permeable membrane, you have pure water molecules. And on the other side, you have a solution where the solute is a large biological molecule like a protein. What happens is the side with pure water molecules hit and pass through the semi-permeable membrane at a certain rate. But water molecules on the solution side hit the semi-permeable membrane at a slower rate because some of the area around the semi-permeable membrane is now blocked by solute particles. So you have an imbalance. More water molecules are passing through and going into the salt solution than vice versa. This can also be explained by the concept of entropy. That's another explanation. What ends up happening is that the level of water in the salt solution side rises, and there's a difference in level between the two halves of the U-tube. That difference in level is measured as a pressure called the osmotic pressure. So here's a typical question. What is the molar mass of a protein if 5.87 milligrams per 10 milliliters gives an osmotic pressure of 2.45 torr at 25 degrees Celsius? So the equation is pi, which is the osmotic pressure, equals MRT, where M is molarity, that's moles of solute per liter solution, not molality. R can either be 0.082 if the pressure is expressed as atmospheres, or 62.4 if the pressure is given in torr. And of course, temperature is the absolute temperature, 273 plus degrees Celsius. So pause your playback, try to get the answer, and then on the next slide we'll show you my answer. Okay, here we go. The molar mass is what we're looking for. That's grams of solute per mole. We have grams as milligrams in 10 milliliters. So we need moles. Pi equals MRT, and pressure is given as 2.45 torr. So we're going to use 62.4 for R, and 298 after we add 25 to 273. Solving for molarity, we get 1.32 times 10 to the minus 4 moles per liter. And we multiply that by 0.01 liters, which is 10 milliliters, to get 1.32 times 10 to the minus 6 moles. So then we divide the grams of protein by the moles of protein, and we get around 4,400 grams per mole. Molecular solutes yield 1 mole of dissolved particles per mole of solid that dissolves. For example, solid sugar dissolves to form aqueous sugar. But for ionic solutes like sodium chloride, for every 1 mole of sodium chloride formula unit that dissolves, you get 2 moles of particles, sodium ions and chloride ions. 1 mole of sodium chloride forms 2 moles of particles. So there's a correction factor for this. For ionic solutions, it's called the Van't Hoff factor, and it's a ratio of the moles of actual particles in solution divided by moles of formula units dissolved. So what do you think the Van't Hoff factor for calcium nitrate in water is? Well, if you chose 3, you'd be correct. 1 mole of calcium nitrate breaks up to form 1 mole of calcium ions and 2 moles of nitrate ions, 3 moles of ions altogether. Now, sometimes solute particles form attractions with the solvent molecules, and deviations from Restos Law can occur, especially in concentrated solutions. And in those cases, the Van't Hoff factor may not be a whole number. So in all these colligative property equations, we can insert the letter I symbolizing the Van't Hoff factor. So here's a typical question. Calculate the molality and Van't Hoff factor for an aqueous solution of 0.5% by weight potassium chloride with a freezing point of minus 0.234 degrees Celsius. And the freezing point depression constant for water is 1.86. The formula, of course, is the change in freezing point, the depression in freezing point, is equal to I times molality times the freezing point depression constant. So pause your playback and try it, and then calculate also I, the Van't Hoff factor. Come back and we'll discuss it. Okay, first, the goal is molality, which is moles of solute per kilograms of solvent. And we're starting at 0.5% by weight, which is 0.5 grams of KCl per 100 grams of solution. So first, convert grams of KCl to moles with the molar mass, and we get 0.0067 moles of potassium chloride. Now calculate kilograms of solvent by taking our denominator in percentage, which is 100 grams of solution, and subtracting from it 0.5 grams of potassium chloride, which gives us 99.5 grams of water, or 0.0995 kilograms of water. So now we can calculate molality as moles of solute per kilograms of solvent. It turns out to be 0.0674. Plugging the Kf and this molality into the freezing point depression equation allows us to calculate I, and the answer comes out to be 1.87.